Boy, isn't this just kind of sad to watch. So hang on a second, because I know that I've shown this simulation before, but just hear me out, because I actually want to make a different point about this. What I'm showing here, of course, is just a single particle bouncing around in this rightmost chamber, and it's fairly uninteresting because it's totally predictable. There's no random motion here. If we can even sort of just imagine the trajectory of this particle, we can predict where it's going to be in the next few seconds. It's fairly easy to tell that this is completely deterministic motion. And if I release the partition here, and we are also patient enough for this lonely sphere, a little speed up.
Come on.
There we go. Either you have the very uninteresting result of having the sphere in either 100% in the left chamber and 100% or 100% in the right chamber. Totally uninteresting. But what happens if we increase the number of particles by an order of magnitude or two? Okay, so now I've gone up to 10 particles in the rightmost chamber, and just by eye, it's quite clear that they're still following deterministic paths. It's very easy to tell where each sphere will be in the next instance of time, just by our human intuition. And of course, if I release the partition, nothing particularly special happens. I can, of course, now have fractions of the particles in the left and the right chambers, but nothing particularly surprising is going on. So let's again increase to another order of magnitude and see what happens. All right, so now I have increased to 100 particles. And what's notable about this scenario, besides the lag, of course, is that it's much harder to keep track. Even though the particles are going slowly, we're starting to enter a regime where we are no longer sort of looking at individual paths. We naturally start to just see the whole collection of particles as one whole. And if we release the partition and are a little bit patient, all right, naturally, and I know, this is the point that I made last time, if you are patient enough, you will start to see that you are approaching a sort of a 50-50 split with some fluctuations around 50% in the left chamber and the right chamber, even though we know that each particle is following perfectly deterministic motion. So let's crank it up one more time by another order of magnitude and see what happens there. All right, so here we are at yet another order of magnitude higher. There are 1,000 particles in the right chamber, and besides the fact that it's very hard for Shockwave Flash to render this, so it's a little laggy. Otherwise, it's just very, very hard at this point for us to keep track of any of the particles. And so apart from the fact that this program is entirely deterministic, we know that there's no random motion here. It still will follow probabilistic laws. It will still follow laws of large numbers, where it will roughly evenly split the particles in 50% in the left chamber and 50% in the right chamber eventually, if we sort of let the program relax. But the point that I really wanted to make here is that we only treat systems as probabilistically when we cannot conceive or keep track of all of the information that's presented to us. So, this particular instance, of course, we know is completely deterministic, but that's just how our minds work. We look at systems like this as probabilistic because we can't keep track of all the information. We talk about things like entropy and the probability in the left chamber and the right chamber. But the problem, of course, is that then we take probability as something that is somehow fundamentally part of the world. So is it possible that on a daily basis we're making the same mistake? When we talk about things as chance or luck or probabilistic, are the underlying dynamics not just completely deterministic like this program, and we just sort of have this on switch for looking at things probabilistically? So let me illustrate this point a little bit further with another program that I have. Okay, so now the point of this program is that you're presented with a selection of the 4 aces, and then one card is hidden in the middle. And what you're supposed to do here is select which of the 4 aces you believe the hidden card to be, just based on your intuition. So let's say I select this one, and we can see, well, okay, that wasn't right. But for the more mathematically inclined, you'll recognize that this is just a binary choice. And if I were to repeat this process n times and have x successes, well, the probability of that outcome is given by the binomial distribution. Now, through Bayes' formula, we can, of course, invert that question and ask what is the probability of the true probability of a success? Or in other words, what's your true rate of successes, just based on intuition? Now that probability distribution, the probability of the probability, or as I've given it in this program, the rate of successes, so the true rate probability, is given in the top right. In Bayesian terminology, this is known as the posterior distribution. So now how does this connect back to what I was just telling you about? And in particular, what does it have to do with an ideal guess? Well, here we have a scenario where a card is randomly chosen, that is the hidden card, and each ace is chosen with 1/4 probability. And our whole process of getting to Bayes' formula through a likelihood function is based on the assumption that this process is indeed probabilistic. And I can tell you, because, well, I wrote this program, that the selection of the hidden card is based on a random number generator. So everything sort of plays out. It seems like a fair assumption that this is a probabilistic process, and that we're testing your intuition for guessing the hidden card. But here's the kicker. As many of you probably already know, random number generators are not actually random. They also follow a deterministic process, but a deterministic process which is very hard to track, so appears to be random. So again, I ask the question, are there actually truly random processes in our daily experience? If we were to do this with an actual card deck, we know that the dynamics of how the cards move throughout the deck as we shuffle is actually fully deterministic. So that would make the scenario even worse. At this point, often people try to invoke something around quantum mechanics. But of course, quantum mechanics doesn't actually make any statements about the nature of reality in terms of whether or not fundamentally the universe is random or deterministic. It just sets a limit on how well things can be known through relations like the uncertainty principle. In fact, if you'd like to know more about deterministic models of quantum mechanics that do reasonably well against experimental evidence, you can check out my friend's channel, Quantum Beables. So there's a little food for thought. If you enjoyed this, please like and subscribe, because it does help. If you'd like to try either of these programs yourself, they are available at pseudosomnia.itch.io. And hey, thanks for watching.